Good morning, everyone, and thank you very much for joining us. Just in case, do you want to confirm, this is the South Coast Conservation Program webinar. Our focus is on species at risk, as is all of our webinars, and this one is focused on the value of indicators. We're going to be looking at using local species and ecological communities to measure and map biodiversity with a specific focus on Metro Vancouver. And I'd like to thank our sponsors and supporters for this particular webinar series. I'd like to thank the Canadian Society of Environmental Biologists who have provided us with the webinar platform for hosting the SCCP webinar series. And also a very big thanks to Environment and Climate Change Canada for providing the funding to allow these webinar series to actually be hosted. A little bit about us, your host. My name is Pamela Zevitt, and I'm the Special Programs Coordinator for the South Coast Conservation Program. And just to let you know that this is actually the 6th webinar that we are having. We will be having one more in the spring of 2019. The focus for the South Coast Conservation Program is to be working with local governments, private landowners, and other land use interests, as well as industry and practitioners across the South Coast of British Columbia. And our focus is on a conservation-based change to protect and recover species at risk throughout the South Coast region. And just for a little bit of geographic context, the South Coast is really the area that goes from around Powell River to Hope and then a little bit northeast to Pemberton. So it is a fairly large landscape with a lot of interesting political jurisdiction issues, as well as an incredibly biodiverse area with a lot of species at risk issues and challenges. If you want to watch our entire webinar series, you can go to our webinar channel. The link is down at the bottom. And this webinar is being recorded, so it will be posted on our YouTube channel. And you can also click on our YouTube channel and link to it through our homepage at sccp.ca. Our first presenter is going to be Josephine Clarke, and she's a regional planner with Metro Vancouver's Parks Planning and Environment Department at Metro Vancouver. And it's a fairly large regional district with 21 municipalities, an electoral area, and one Treaty First Nation, which is Tsawwassen First Nation. The collaborative plans for and delivers regional scale services. Josephine is a registered professional biologist and GIS specialist, and her work focuses on environmental planning initiatives to tackle complex ecological challenges that cross jurisdictional boundaries across the region. The current projects that she's involved include mapping sensitive ecosystems, developing ecological health indicators, and quantifying ecosystem services. So Josephine, I'm just going to unmute you now, and then I'm going to give you the little wand to hand over.
Fantastic.
Okay, and you can get started as soon as you want.
Okay, you can see my screen?
Sure can.
Okay, awesome.
The one thing that you might want to do is you're actually seeing you set up in slide view mode as opposed to presenter mode.
Okay, let me see if I can...
Click on that one.
No? What are you seeing?
Oh, you might want to, it looks like the monitor thing is, you see that? Click on that and see what that does.
Nothing good. No.
Are you using 2 monitors?
Yeah, I am.
Okay, so you've got it to actually, when you accepted it, you actually have to go to the correct monitor. So it's the one that you're not using right now.
Okay. I have no idea how to do that. I'm really sorry. This is not my normal setup at all. What can I do? Display.
Okay. What I'm going to do, I'm going to go back. That's perfect. Yay! Okay.
Hooray.
All right.
Okay.
And away we go. I'm muting myself.
Okay.
Right.
So I'm going to kick things off today by first setting the scene a little bit, talking about what we mean by indicators. What are they? How are we using them? And then I'll look at the data sets we've been using to develop indicators and highlight some of our findings so far. I'm then going to hand over to Sara at the Landscape Ecology Lab up at UBC. Sara has a long-term research interest in using indicators and thinking about how they can be used to further the integration of land use and conservation planning. And we've been lucky enough to work with Sara and her team on a couple of different projects, and she's going to look at these in a bit more depth. So first off, what are indicators? What do we mean when we say something is an indicator? In simple terms, indicators are something that we can measure and track that tells us something about the state or condition of an aspect of the environment. And for our work, we're mostly thinking about landscape indicators, so a feature of the landscape that we can measure, usually remotely, using aerial or satellite imagery, perhaps LiDAR data. And examples of landscape indicators would be canopy cover or impervious surfaces. So taking the canopy cover example first, by measuring the amount of canopy cover, we're gaining information about a range of ecosystem services provided by trees, such as amounts of stored carbon, how much vegetation there is to capture rainwater, how much wildlife habitat is available, and how much of our city streets are being shaded on hot summer days, which has the effect of reducing the urban heat island effect, which is where our cities are considerably hotter than surrounding more vegetated areas. Another common landscape indicator measured is amounts of impervious surfaces, and impervious surfaces prevent water infiltrating into the soil and so can result in increased runoff and the potential for flooding, as well as decreases in water quality as pollutants are washed off of paved areas and into streams. So higher levels of impervious surfaces typically mean more stormwater runoff and lower water quality. It also, more impervious surfaces results in increased temperatures, so more of this urban heat island effect. So by measuring these features of the landscape, we can obtain information about the state of various aspects of the environment in an easier and cheaper way than if we were directly trying to measure all these things. And then by repeating the measurements over time, we can track how they're changing and hopefully gain information to help us develop suitable responses. But first, to back up a little, I wanted to take a minute just to talk about who Metro Vancouver is and why we're interested in indicators as an approach. So as Pamela said at the beginning, Metro Vancouver is a federation of 21 municipalities, one electoral area and one treaty First Nation, and we collaboratively plan for and deliver regional scale services. We provide core services of drinking water, wastewater treatment and solid waste management, and we also regulate air quality, plan for urban growth, manage regional park system and provide affordable housing. So both as an organisation and as a region, Metro Vancouver recognises the importance of ensuring a healthy and resilient natural environment. We have the recently adopted ecological health framework, which lays out how as an organisation we can protect and enhance ecological health through our functions and services, as well as by supporting our members and their efforts. And then Metro 2040, the regional growth strategy, sets out the collective vision for how our region is going to grow. And it provides us a framework for land use planning, including for the environment and climate change. And some key ways that Metro 2040 aims to enhance ecological health are through strategies on protecting conservation and recreation lands and protecting and enhancing natural features and their connectivity. It also focuses development within the urban containment boundary with the aim of avoiding sprawl that can consume natural areas. So why are indicators a useful approach for Metro Vancouver? A key reason is that indicators are cost effective for large areas. Metro Vancouver is about 280,000 hectares in size, and so it can be prohibitively expensive to collect data relating to ecological health for this whole area. So we can use indicators as an additional information source or as a complement to existing field sampling, which is often time consuming and costly. Also, landscape indicators, they provide information at broader spatial scales. So it means that we can compare between different areas and get a much more complete understanding of what's happening across the whole region. It's repeatable. So using this approach, we can repeat it at intervals and monitor how indicators are changing over time. And it allows us to look across jurisdictional boundaries. So as the region, our focus needs to be on looking across boundaries to help provide that broader view that perhaps an individual municipality may not have. And finally, they're usually quite communicable. So things like canopy cover, for example, it's a fairly simple concept. People understand it, even if they don't know about the many different ecosystem services we're considering when we measure it. So they're useful for communicating to a wide range of audiences. So we want to use indicators in two main ways. Firstly, to help us with reporting and monitoring. We can use them to help provide information for state of the environment reporting and monitoring for the region. So help us understand how are we doing? Where are the main areas of concern? It also helps us to assess whether we're meeting the goals set under Metro 2040 relating to the environment. And then secondly, they can be used to inform policy and planning, both at Metro Vancouver and also for our members in their work. So in order to develop and measure indicators, you need data. And in this case, we need data for the whole region. And ideally, if this is to be a cost-effective approach, we needed data sets that we could use for multiple indicators or purposes. So today I'm going to talk about two key data sets that we created for Metro Vancouver. Firstly, the sensitive ecosystem inventory, which maps the region's most ecologically important areas. And then secondly, a high-resolution land cover classification. And these provide us with consistent data for the whole region, which enables us to measure indicators in a number of different ways and at a variety of scales. So regional scale, sub-regional, watershed level, for example, and then we can compare between different areas. So the SEI maps areas that are ecologically sensitive, rare, at risk, or important for biodiversity. And we map several classes of sensitive ecosystem, for example, old forest, wetlands, alpine, estuarine, riparian classes. And then each of these classes is broken into subclasses. So for example, for wetland, we map bogs and fens, marshes, shallow water, swamps, etc. And these sensitive ecosystems are mapped as small as 1/2 hectare, which is pretty small for a regional scale inventory. And we also map a few types of what are called modified ecosystems. So these are typically younger and more human modified, but they still have a lot of ecological value. And they're particularly important in places where we've lost a lot of the sensitive ecosystems. We don't map all modified ecosystems, so only certain classes, namely young forest and old field habitat. And we only include larger occurrences of these ecosystems. So for example, for young forest, patches have to be over 5 hectares to be included. So we're mapping the best examples of these types of ecosystems. And the inventory was originally released in 2013 based on 2009 orthophoto imagery. So as well as knowing what is there, we also needed to know something about what state it's in. And for each polygon, there is an assessment of what we termed the ecosystem quality. And here are two examples that show the range of states observed and mapped. So on the left is a high quality site. It's in good condition, it's a decent size, it's surrounded by other natural ecosystems. And on the right is a lower quality site. It's smaller, there's evidence of disturbance within the site, and it's surrounded by development. And the majority of ecosystems found in the places where we live are disturbed to some degree. So the SEI was originally based on 2009 orthophotos, and using this, it enabled us to report out on how many hectares of different types of sensitive ecosystems were remaining in the region or sub-region and what state they're in, using the quality information that I just talked about. But we've recently completed an update using 2014 orthophotos, and now for the first time we can look at change. So what's happened over that 5-year period to the region's most important ecological areas. And now, rather than having just static figures on total hectares, we can quantify the amount, rate, and type of any losses that occurred over that period. And I'm going to briefly discuss some of the results here. So in reporting out the results, we usually refer to two main areas. We look at the full region and then the regional core, shown here in hatched. And this is the more urbanized southern part of the region. It excludes the large protected areas in the north, the estuaries, and the other high elevation areas. And it's really intended to give us a clearer view of what's happening in the areas where local governments are making decisions and actions are going to have the most impact. So presented here are a summary of the overall results. The graph shows the total loss for sensitive and modified ecosystems at the top, followed by the 5 classes with the greatest losses. So mature forest, young forest, old field, wetland, and riparian. The red bar shows losses for the region, and the grey shows losses within the regional core. And total losses for the region were just over 1,600 hectares. So that means that we've lost about 1% of the region's sensitive and modified ecosystems over the last 5 years. To put that into perspective, that's the equivalent of losing about 4 Stanley Parks in 5 years. So for the regional core, losses were just under 1,200 hectares, which means we've lost 3.4% of sensitive and modified ecosystems in the regional core over the last 5 years. And to focus in on forests for a minute, mature and young forests saw the greatest losses of all ecosystem classes at the regional level. So that's forests that are older than 30 years and younger than 250 years. And these are the oldest remaining forests outside of the higher elevation protected areas where there's still a lot of old forest left. But the region lost almost 1,000 hectares of these forests in 5 years, which is about 2%. And for the regional core, it was about 3.5%. So we're looking at a particularly fast rates of loss for our forest ecosystems. So these are what you might call the kind of the headline results from the update. We're now looking at how ecosystem quality has changed over the 5 years, as well as trying to understand the loss a bit more. So for example, what was the loss to in terms of land use, and how do things look at the sub-regional level? And we'll report out on those over time. So that was the SEI, detailed information about the most ecologically important places. The second key data set is the high resolution land cover classification for Metro Vancouver. And this is a complete regional map showing what is on the Earth's surface. So is it buildings or paved? Is it grass, herb, shrub, coniferous or deciduous tree? And because this layer gives you a complete surface, it's very useful for any analysis where you need to know about the entire landscape. So to create this data set, we worked with the Integrated Remote Sensing Studio at UBC, and through their expertise, we were able to take advantage of up-to-date GIS techniques which combined using 5-meter resolution satellite imagery with LiDAR data wherever it was available. And the areas where we had LiDAR are outlined in blue on the map on your screen. And LiDAR gives us this detailed information about the height of objects on the ground, and it really helps to improve accuracy. So here's a close-up look of an urban area where we had LiDAR, so you can get an idea of the level of detail. You can see that the street trees and small buildings such as garages are captured along with some lawn areas. And the ability to use high-resolution imagery along with LiDAR is particularly important in urban areas such as this, where what's on the surface changes so much. It's a very heterogeneous landscape. So the land cover gives us this view of the whole landscape, which makes it a very useful data set for a number of different purposes. We're just starting to delve into using the land cover to develop and measure some indicators, but here is some initial work that we've done, first looking at canopy cover. Here we have canopy cover at a few different scales. So at the regional scale, we calculated canopy cover to be 52%, driven largely by the extensive forests to the north of the region. For the regional core, shown on this map as the darker area, it's 33%. And finally, for the urban containment boundary, shown here in hatched, and just as a reminder, this is the area established by Metro 2040 as the long-term stable footprint for growth, so it's intended to avoid sprawl. And here the canopy is 32%, so not much lower than the regional core. And this is another view of canopy cover, here presented as a percentage by block within the urban containment boundary. So areas of low canopy typically coincide with urban centres and commercial and industrial land uses, which is probably not surprising. But when you consider that these are the places where a lot of people work and live, that means that they're missing out on the many benefits that trees and tree canopy would provide. And here we have levels of impervious surfaces, again measured for the region, the regional core, and the urban containment boundary. Unsurprisingly, the urban containment boundary, where urban development is focused, has the highest levels of impermeability at about 50%. The regional core has 31% and the region 20% impermeability. And again, we have this information displayed as a percentage by block for the urban containment boundary. And so typically areas with low canopy tend to have high imperviousness. So again, urban centres and commercial and industrial lands came through as the areas of highest imperviousness. So as well as not receiving the benefits of tree canopy, these areas are receiving the disbenefits of high imperviousness. So hotter temperatures, increased potential for flooding, etc. And climate projections for this region show that we're likely moving towards hotter summers along with increased rainfall, more frequent and extreme storm events at other times of the year. So areas with low canopy and high imperviousness are likely going to be more vulnerable to these impacts. So this is the first time that we've had a high resolution land cover, so we don't have any change data yet, but our intent is to update this in a few years along with the SEI, and then we can look at change in canopy and imperviousness over time. So just to finish off my bit, we've identified a broad range of applications for these data sets, some of which we've just looked at today. So indicators and monitoring, we're already tracking amounts of sensitive ecosystems in the region and how that's changing over time. We're working on canopy cover and impervious surfaces. We've also been looking at ways to measure green space connectivity and using landscape indicators to measure aspects of watershed and stream health. And this has obvious connections to integrated stormwater management planning work, and we hope it will help us to look at that link between terrestrial and aquatic systems, and Sarah's going to talk more about these next. But the data sets can also be used to inform land use planning, parks planning and management, stormwater management planning, drinking water resource management. We think they're also going to be very useful to look at green infrastructure planning, so identifying where are there opportunities to increase green infrastructure and where should be a priority to do so, etc. This data could also be used to explore climate vulnerability, so for example by overlaying it with information on vulnerable populations. And finally, ecosystem services assessment. We want to be able to map, quantify, and generally have a better understanding of the provision of ecosystem services across the region. And the land cover in particular is a key data set for this because of its whole landscape view. So that's everything that I have for today. I'm happy to take any questions before handing over to Sarah.
Thanks very much, Josephine. And just a reminder, if you can enter your questions into the question component in your side panel, that would be lovely. You can also use the chat box. And we actually do have a question from Erin Clement, and she asks, would levels of protection on the land have any impact to the level of sensitivity given to the area? This could help focus on more vulnerable areas.
So it doesn't affect our assessment of sensitivity. It's we're really looking at ecological sensitivity for that assessment. But you're totally right in that layering over it, looking at where's protected and where's not protected, is sort of a different element of sensitivity. So absolutely, that's another piece of the next step assessment that we want to do. So where are sensitive ecosystems not protected currently, and I think what are the proportions for each sensitive ecosystem class that are protected or not protected, so we can see whether there's certain classes that are underrepresented in our protected areas network. Yeah, definitely important.
Yeah. And Josephine, I do remember way back when, my years working on the Metro Vancouver biodiversity strategy, that one of the things we did through the provincial side of mapping was to actually create a layer of all the protected areas. It was part of a gap analysis.
Yeah.
And, so, I mean, does Metro still have those old GIS layers?
We actually do have a more up-to-date layer than that.
Good.
Yeah, no,
Better.
it's very sweet. It does need a bit of further work though. I think it's a bit of a complicated one. I mean, without getting too deep into it, thinking about, what do we mean when we say protected area? What's in that layer and what's out? How protected is it to be included? That kind of thing. So it's not a totally simple exercise, but yeah, it is something that we have something to work with, and we want to improve it over the next year or so, I'd say.
Okay. And we have another question from Adrienne Pollard. And she asks, did you use the provincial or federal SEI mapping as a starting point?
Absolutely. So the SEI, the provincial SEI has standards associated with it, and we used those standards to develop our process and our methodology, and we worked with the provincial ecologists in designing our projects. Yeah, that was really a major reason why we picked doing an SEI as opposed to another mapping method, is because we recognize that it's an established process. There are other SEIs around the province, including sort of adjacent areas such as the Sunshine Coast and Sumas Mountain, etc.
And in regards to the SEI mapping, I know that one of the challenges that they had when they did all of the sort of the first generation of SEI mapping on Vancouver Island, which I think was the first jurisdiction to do it provincially, a lot of things that they found was that municipalities were actually housing that data, but they weren't necessarily using it to actually ensure that areas were flagged as part of land use decision making. And so when they went back to do the update, which is what you've done to measure loss, they were kind of like, well, what's going on? Why aren't you using this effectively to protect these areas? Because they were looking at all that sometimes big chunks that had been eroded away through development that were clearly identified as sensitive ecosystems.
Yeah. So, I mean, one focus of mine over next year, I think, is to work a bit more closely with our members to make sure that they have all these different data sets that we've been creating, that they understand how to use them, and that we get feedback from them as what can we do to make these things more accessible and usable, because ultimately that's how it's going to be. That's how it's going to be useful if our members are taking it on board and incorporating it into their work.
Yes, and I would say, obviously, the main focus for the South Coast Conservation Program is especially where critical habitat mapping is available, to make sure that gets identified and used appropriately in land use processes. Greg Ferguson has a question about the data sources, and he asks, what was the high resolution data that was used, and is this available to others and for other areas?
So the high resolution dataset was the land cover, which is 5 meter resolution for the entire region, and 2 meter resolution in the areas where we had LiDAR, which is most of the urban areas. It is available at the moment. You have to just come to us and set up a data sharing agreement, although we're working towards having it on our open data site. I'm hoping next year. As for is it available in other jurisdictions, I'm assuming meaning sort of nearby jurisdictions, not that I am aware of, but I'm honestly fairly focused on Metro Vancouver, so I may just not know.
Well, I remember some of the original data sets that we developed through the regional work with the province was actually coming through a partnership with Simon Fraser University.
Oh, yeah.
So I know they were initially taking a look at various types of remote sensing imagery. At the time, it was very expensive, so we were kind of looking for the best bang for the buck, and I just marvel at how things have changed in that 15 years or so.
It's even in sort of a 5-year period. It's this higher resolution imagery it's suddenly accessible to us. Like we can afford to do it at the regional scale, which is kind of a game changer, I'd say.
I have a question from James Casey. For waterfowl, one of the key habitats is agricultural lands with in-soil crops. Have agricultural lands been considered for the modified habitat classes?
Yeah, good question. So the first time round, when we did the SEI, we included the seasonally flooded agricultural fields class, which is sort of part of the standard SEI suite of classes. And we made efforts to map it using the imagery that we had and a reasonable amount of field work. And then we came back to try and update it, and we just found it extremely challenging because our imagery is obviously just sort of one point in time, and depending on when your imagery is taken, it might be, you know, a little later in the year, so it's not showing as wet, or it might be a particularly dry year, and we were finding that we could not accurately go back and the areas that looked wet or dry were different to what we'd found the first time round. And we actually felt that the accuracy was so poor that we couldn't keep that class in there. Not that we don't think it's important, but just we don't feel that we have the ability to accurately map it. So I think we need to give some more thought as to what we could do with that, and we're open to any suggestions.
Okay, and I've got one question from, sorry, they don't make these boxes very big in regards to actually being very quick. So it's a little teeny thing that I've got to scroll through. So. Okay, and I had a question from Katerina that I asked her to elaborate on in regards to the species indicators that were being selected. So Katerina, if you can pop that question back in with a little more information, that would be great.
That might come through a little more in Sarah's presentation, I think.
Oops, I think she's just coming through to answer it. It's good to see a lot of chat going on.
Yeah.
Really appreciate that. Okay, so what I'm going to do is, again, please feel free to populate the question box with questions. And what we're going to do is move on to Sarah's presentation now. Josephine, I'm just going to mute you now, and then I'm going to open, Sarah, I'm going to open up your microphone. Sara Google is an associate professor in the field of landscape ecology and conservation with the University of British Columbia's Landscape Ecology Lab, which is part of the Forest and Conservation Sciences program. And I should add that the South Coast Conservation Program is actually chaired through John Richardson, who is with that Forest and Conservation Science program as well. Sarah's work focuses on applying spatial analysis tools for solving pressing and emerging problems in environmental science. Much of the strength of landscape ecology lies in its ability to address challenges over large areas, over spatial and temporal scales at which decision-making often occurs. While spatial dynamics have long been fundamental to terrestrial conservation strategies, land management, and reserve design, mapping and spatial themes are increasingly recognized as important for ecosystem management in aquatic, coastal, and marine systems. So Sarah, I am going to hand presentation over to you.
Okay.
And take it from there.
Okay. So hopefully everyone can see my screen okay?
Yep.
And it should be the PowerPoint?
There you go. Yeah.
Yeah, we're good. Okay. Well, thank you for inviting me to share our work today. And of course, special thanks to Josephine, because part of what I'm going to talk about today was originally spawned as part of a collaboration with Josephine Clarke. So I hope these are some tools and approaches that are useful to think about how we manage landscapes for more than one thing. So managing landscapes for multiple purposes, multiple ecosystem services, and multiple species is really challenging. It's even more challenging when you try to simultaneously manage for terrestrial as well as aquatic benefits. And so that's what I'm working towards with this work, is coming up with some landscape indicators that help us understand what's happening in terrestrial systems, but also provide some information about what's going on in aquatic ecosystems. So that's the overall purpose of what we're doing. And Josephine already did a great job of talking about what what indicators are, and that they're useful for quantifying the status of any system, and that you can use them to compare over time and across different locations. And what I'm going to go further into today is remote sensing based indicators that give us information about land cover. And there's been several decades of work using land cover as an indicator of aquatic systems. And so we're developing those further for urban streams and figuring out when they work and when they fail, and how they can help us improve. What do we have to add to indicators to help indicators do a better job of predicting stream status? And so why I find this interesting is because it's, as I said, it's really hard to plan for terrestrial ecosystems at the same time protect aquatic systems. And so if we can come up with ways to plan for these things simultaneously, hopefully we can be more strategic in our land management decisions. And so, as Josephine mentioned, we know that increasing levels of impervious surfaces in urban systems are expanding rapidly, and this can lead to problems with excess stormwater runoff that impacts water chemistry as well as stream biota. And we know that urban vegetation and green infrastructure more generally can help alleviate the impacts of expansion of impervious surfaces. And so the question remains then, if we're going to protect green space or we're going to add more green space, where can we put it so that the impacts of impervious surfaces are reduced as much as possible? And that's all made even more problematic when you're trying to deal with what do terrestrial systems need and what do aquatic systems need as well. So some of you might have a bit of experience with integrated stormwater management plans, and so they often use indicators. So these ISMP indicators look at things like percent total impervious area in a watershed. Another indicator that's used is the percent of riparian forest integrity, which is basically how much of the riparian zone has forests in it. And so we've been using these ISMP indicators and comparing them to our own landscape indicators to see if our own landscape indicators do a better job of predicting what's going on in streams. And so just to make the take-home message right up front and simplify it a bit, we found that the conventional ISMP indicators explain at most 30% of what's going on in streams. If we build regression models using impervious surface to predict the status of streams, and some of the percent riparian forest integrity indicators explain less than 5% of water chemistry or biotic indices of biotic integrity. Whereas what we found is some of our newer landscape indicators that have additional features, we can explain approaching 60% of the variability in in-stream biotic indicators. And so what this tells us is that there's room to improve on existing indicators, such as ISMP, with new features, new characteristics of the landscape that we can add into indicators. So what I thought I would do is just tell you a little bit about what those things are that help make landscape indicators better, and just give you a short summary of what that has taught us so far. So one big improvement is the fact that landscape indicators are now at a higher spatial resolution. And so thanks, Josephine, for explaining the high spatial resolution land cover map that we've been using for some of this work. And having information at 5 meters and in some places at 2 meter scale can be really helpful for identifying urban features, which are often missed when we use coarser resolution imagery. So just to kind of emphasize that point a little more, these two images on the right, the top image is the same location mapped using 30-meter imagery, such as Landsat, and then the bottom area represents the same area, but mapped using this new resolution imagery at 5 meters. And so you can see how the features are represented very differently at a different scale. And so in terms of understanding impervious surfaces, which are so critical to urban stormwater runoff and all these other ecosystem functions, we were finding that the 30-meter map in the region generally overestimated impervious surfaces, in some cases by about 85%. So it overestimated how much impervious surfaces there were, in part because the coarse resolution map misses important urban features like trees and small forest patches. Small patches of green space can just be entirely missed. And so if we don't even know how much green space there is, and we don't know accurately how much impervious surface there is, that makes it really hard to develop reliable indicators. So we were happy to see some of the benefits from a 5-meter resolution map. And so when we actually create landscape indicators, we can measure the composition of the land as well as how it's arranged. And so the first thing, the easiest thing to understand is these compositional indicators. So this is just percent or proportion of impervious surface, or the percent proportion of conifers or deciduous forests. And so we might calculate these things just within the watershed, the contributing area of a stream, or just along the riparian zone. So one of these images shows the yellow riparian zone delineated. And so figuring out whether, when you're predicting some stream quality attribute, trying to decide whether the best prediction comes from this riparian zone area or the entire watershed is kind of one of the first questions one might ask. And so you might use percent impervious surface at the watershed and compare it to percent impervious surface in the riparian zone and see which makes a better prediction, see which one has a higher, stronger correlation with a water quality or an in-stream characteristic that you're interested in. And so that's what's commonly done, and there's a few decades of work using these percent cover indicators. And then what's a little bit newer is incorporating configuration. And so here's a little silly schematic showing you the different ways we can quantify the configuration of the landscape. So for this first example with fragmentation and patch density, the proportion of green space, the total area in green space is the same, but you see the arrangement is quite different. Is it one big patch or several small patches, right? So we can come up with indicators that capture that. Similarly, another index we might use is the largest patch index. And so that might give us an idea of, well, both these watersheds have 4 patches of forest, but one of them's quite big and large. And it's often an indicator simply of the largest patch in a watershed can be a pretty good predictor of some water quality and biotic variables as well. The other thing we might want to capture is the perimeter area ratio. So here's an example of a contrast with an area that has the same amount of green space, but on the left you see a lot of edge perimeter habitat, whereas that habitat could be in one large clump. And so you might want to incorporate that. So that's beyond just the total amount or the total percent of land, but how it's actually arranged. And then the last thing is there's a bunch of different ways we can measure contagion or interspersion. And so that's the idea of whether land cover is in 1 or 2 clumps, like it is here on the right, or whether it's dispersed and all different cover types are kind of interspersed together. And so we have some landscape metrics that help us characterize those things. And then that helps us, for example, this picture here on the right then shows you a landscape, a zoom in of the high resolution imagery, and it kind of conveys some of these differences. So the landscape on the top, you see the impervious surfaces are in red, and coniferous and deciduous are 2 different shades of green. And you can see, even if you have similar amounts of green space, its actual configuration can vary wildly. So the image on the bottom has a much higher largest patch index, has a lower overall perimeter to area ratio, higher edge aggregation, less overall edges. And so these are all the kinds of things we can quantify using landscape indicators of configuration. So basically, for landscape indicators, first you want to know, should I measure the landscape in the whole watershed or just in the riparian zone? And then the second question is it enough to just track percent cover, or do I need to know configuration, like in some of these examples here? And my screen seems to not want to go to the next slide. So
Sarah, it might just be one of those little hiccups that happens with PowerPoint. It may just be due to the data heaviness of particular slide. Can you go backwards?
Let's see. It's weird. It's not even letting me escape from my. Let's see if this will work. Okay. So if I have to do it manually, then that's what I'll do. So in order to develop some landscape indicators, then, right, as I mentioned before, we're doing this for a starter, very stream focused. And so part of that involves some stream and watershed delineation. So we created a newer, improved high spatial resolution DEM across the landscape. And through this, we were able to generally delineate some of the major watersheds. In addition, we were provided stream layers from Josephine and her team throughout Metro Vancouver, and you can see that in blue. And then in green, you see some of the water quality monitoring stations that we were able to access data from. And so what I'm going to show you today is based on part of the region. If any of you online today are interested in becoming involved and having your site included in indicator development, we're always looking for additional data sets and additional indicators to use. And so while we started with a fair amount of data for the region, what we then had to do was associate the contributing area from each monitoring station with the upstream watershed. And then we also had a fair bit of work to do in terms of correcting the stream layer. So in some cases, the stream layers were not even connected from the headwaters downstream. They were choppy and blocked apart. In some cases, the stream layer didn't quite match the high resolution imagery because it was digitized, too far to the left or the right. So there's quite a bit of error correction that we had to do. So ultimately, we ended up with no more than 63, a sample size of 63 streams and their associated watersheds. And we started looking at in-stream, a wide variety of in-stream indicators, starting with some water chemistry variables, looking at nitrate concentrations, dissolved oxygen, fecal coliform concentrations, as well as E. coli. And that was work with Josephine and her group. And then we've had some more recent collaborations where we're looking at in-stream biotic indicators. And so with that, we focused on benthic macroinvertebrates. And so we're looking at BIBI, so that's the benthic indices of biological integrity, as well as taxa richness and percent EPT, which is a nice indicator, as well as percent oligochaetes, which give us some idea of, in terms of the macroinvertebrates, the benthic macroinvertebrates, how they're doing in streams. And then we're just now starting to look at heavy metal concentrations as well. So just some of the take-home messages so far. So we found that percent impervious surface was in general a good indicator, but the edge to area ratio, so that's that perimeter to area ratio that we talked about, the configuration was really important in explaining some of these variables. And so we were able to explain in wet season about half the variability of dissolved oxygen and fecal coliform concentrations. And then about 60% of the variability of benthic macroinvertebrates, depending on whether we use percent EBT and percent oligochaetes. The other thing we were able to spend some time improving is how much does the forest, determining how much the forest classification scheme actually mattered. And so for example, indicators used for ISMPs generally lump all forests together. So deciduous and deciduous and coniferous forests would be just clumped into a generic forest class. For some indicators, that works just fine. What we found, though, is distinguishing coniferous and deciduous forests did a better job for taxa richness. So in that case, it improved the explanatory power, and we were able to explain about 50% of the variability in taxa richness in streams. So depending on the scale of information you use and whether or not you use arrangement and whether or not you use a slightly different forest classification scheme, that can affect your results. And so what we're in the process of doing is figuring out which response variables, which in-stream response variables are most related to which type of indicator at which scale and which classification scheme. And so as I mentioned, we're interested in expanding to new streams and watersheds. So the more information we have, the better indicators we can build, and the more we can use these indicators to extrapolate to new areas, because we want to represent very urbanized watersheds as well as more suburban, as well as more agricultural and even more pristine watersheds. So the more watersheds and sampling points we can add, the better information we'll get. We're also interested, if anyone's, let me try to move this thing. If anyone's interested in thinking of new ways to communicate with the public about water quality. And so what we did as a little fun thing was just set water quality parameters to music. So this is basically nitrate concentration set to a scale. So that's a clean river. And here's one with a little bit more pollution, nitrate pollution. Let's see. So pollution sounds like jazz. I guess that's what we've learned from that. But what we're interested in doing really is finding new ways to share this type of information with the public. What do different streams, they might know what different streams look like from the air. We're thinking about new ways to do that. But also if we can listen to stream health, that might be a new way to communicate with communities about the health of their streams. So that's more of an outreach activity that we're interested in, looking for more collaborators to do more of that. Some things we're also doing next are in terms of looking at in-stream predictors, or looking at landscape predictors of in-stream heavy metal concentrations. We're adding in road densities. And so this is just a schematic to kind of show you what that looks like. So basically using road maps for the region, we can get a road density estimate for each pixel or each cell. And so what we want to do is add to our landscape indicators so that a given watershed has a road density metric as well. And there's a variety of reasons why that might be particularly helpful for heavy metal concentrations in streams. And we seem to be stuck again. Let's see. Okay, and so here's a visual of flying across some urban-rural gradients throughout the region. So I think looking at the spatial heterogeneity and how it changes, how the forest and impervious surfaces changes as one moves along a stream from the urban to suburban to rural gradients, gives you a real idea of the complex spatial pattern, the relative amount of impervious surface versus forests, and in the case of more agricultural watersheds, the relative abundance of different farming activities and existing riparian forests. And so my current PhD student, Jennifer Wang, she's interested in exploring landscape indicators across this gradient, right? So it's really likely that the type of landscape indicator that works in an urbanized environment might be quite different than the best landscape indicator that works more, that's most useful in an agricultural setting. And so she's interested in looking at those differences across the landscape and figuring out, is it helpful to think of more rural landscape indicators versus urban landscape indicators, or can we use the same landscape indicators in either setting? So that's what she's going to be focusing on. And lastly, I'll just say a few words about landscape connectivity and why we're going to be looking at that and incorporating that into our landscape indicator approach. So I'm not sure if I can move this thing, so it's just, this little bar is going to be in the way. So what you're looking at here, this is just a silly schematic that shows you what how you can represent a landscape as a network. And so what you're looking at here is each of these little dots represents a patch or a node. And then these connections, these links, show which nodes are connected, right? So this is just a way to represent how an animal, an organism might move through the landscape. What's really interesting and useful about a network analysis is it gives you additional information about connectivity in kind of surprising ways. So if we look at this, I hope you can see my mouse. So if you look at this patch right here, there's two small nodes right here that may be very small habitat, and they may show up as low quality according to, say, an SCI classification. So they may not show up as being very important. But these two spots are really critical for overall landscape connectivity. So getting from one end of this red patch to the other, there's really no way to get from one end to the other without going through those two habitat patches there. So while they might not have good attributes from the standpoint of habitat area, they might be small patches, they might be really degraded patches, but you can see from this network that they're important as a stepping stone to connect this whole area down here with this whole area to the north. And so networks are really good at getting at these kind of things. So it's could be a small stepping stone patch that otherwise would be missed from conservation planning because it's small, it's not super useful, but it might have really important stepping stone functions. And so networks can help us look at things like that. So what we're in the process of doing is building a bunch of networks for different species throughout the region. And here's just an example with Pacific wren and Douglas squirrel and Townsend's vole. And what you can do once you build a network, you can rank patches by how important they are to network connectivity. And so these are just some schematics that show you what that might look like. So you can give patches different colors that tell you, if I lose this patch, it's really important to overall connectivity. And we have ways to quantify that using different network metrics. We can also look at connectivity relative to their protection. So here's just an example. The things with red circles show you important connectivity hubs that are unprotected, right? So we can build a map of connectivity and figure out, are there important places for connectivity that are not yet protected, and can we use that to help our planning? Similar example as well, just showing you a different network map that shows you where the connectivity hubs are and where are the ones for a given species that are not yet protected. And ideally, this is used, so we've just done this so far with 3 species. It's a useful approach because you don't need a lot of data. So in terms of, you don't need a lot of species-specific data, you just need some basic habitat characteristics and a little bit of knowledge about their dispersal ability, and you can build different networks for different species. And so what we're in the process of doing now is expanding this to more species so we can get an idea of where the overlap or mismatch of hubs are throughout the landscape. So how do all these things connect together then? So how does the connectivity work link to the indicators? So what we eventually want to do is think about how we can use landscape indicators for streams and link that to terrestrial conservation planning. And so here's a few ways that I think this could happen. So first of all, we might think about the areas of overlap between the best areas that serve as connectivity hubs and the locations that are important for aquatic protection, right? So maybe those largest patches in the watershed, if the large patch indicator is really important for aquatic systems. And we also find that some of those same large patches are also serving as connectivity hubs and they're not protected. That could be a good way to think about conservation in terrestrial and aquatic systems simultaneously. It also helps us think about where could we protect urban green space where it might be most beneficial to streams, right? So are there certain watersheds where percent impervious surface is really high? And those might be the streams and watersheds that really need the most protection. If our indicators tell us that arrangement matters, that configuration matters, like these perimeter to area ratios, this can help us arrange urban green space in a way that best helps streams. So how much should we put near riparian zones versus upstream areas? It helps us these indicators give us some idea of where in the landscape we can potentially arrange different features to get the most bang for our buck in terrestrial and aquatic systems. I think the indicators approach also helps us think about thresholds. So what we'll be testing is whether there's threshold responses in streams. So what I mean by that is there's some suggestion from the literature that once a watershed surpasses a certain proportion of impervious surface or a certain proportion of forests, that the conditions in that watershed change greatly. So if we have some streams that are near that threshold where just a little bit more green space could potentially put them into a healthier threshold, we might prioritize additional green space in those areas because we know that perhaps we can add connectivity for terrestrial species, but also bring that stream and that watershed above that threshold and into a better system state. So those are some of the ways we can start thinking about aquatic indicators and terrestrial indicators. So lastly, I just want to thank some of the collaborators and the students that have worked really hard in this work, as well as Josephine Clarke, who helped start much of this work. And then we've continued to collaborate with Patrick Lilly from Carewood Liddell, and also thank different NSERC agencies have also helped fund this work. And so I'm happy to take questions that you might have about what we're doing and what we're going to do next.
Great. Thank you very much, Sara. It was gratifying to see a lot of this information finally coming together after such a long process that Metro Vancouver has been involved with in regards to sensitive ecosystems and biodiversity conservation. And I think that the more that we actually start integrating these various types of components to build that holistic picture, the more information that's going to be available to land use decision makers to actually be making more comprehensive decisions because they have the data available to them. And it used to be that it was really hard to get a hold of this. Josephine referred to the fact that it was pretty costly to do remote sensing analysis and a lot of the types of modeling that that we're doing now. And I see that having such a profound effect, I think, on the choices that we're going to be making. So in respect to questions, if you have any questions, please go ahead and put them into the question box, and I will do my best to make sure that they get answered. I know that Katerina had asked a question about using specific species as indicators, and so you referred to that near the end of your presentation, Sara. So what are some of the other species that you think are going to actually be going into this process?
Well, it's a bit of a mixture of talking to people like Josephine as well as Nick Page, who've advised us on what useful species might be, in combination with student interests. So right now we've got a couple of students in our Masters of Geomatics that are interested in trying this approach out in a small pilot area. So I think what they're going to be focusing on are some invasive species, so looking at spread of invasive species across the landscape. Another one, a student in particular is interested in looking at some urban wetland connectivity within the context of bullfrogs, for example. So we're at the stage right now where it's a bit of a proof of concept. And so we're for sure interested in feedback or ideas for additional species where we have a reasonable understanding of their habitat requirements and a somewhat reasonable guess as to dispersal requirements. Because if we have those two things, we can build a network for almost any species.
Right.
I think it's worth pointing out that for the species that we've already run the analysis for already, and we have these networks for, those same networks will apply to other species that have similar habitat requirements and dispersal distances and barriers and so forth. So I'm kind of seeing them as like kind of like archetypes. What I'm hoping that we'll end up with is sort of identify this kind of series of archetypes with maybe a particular species headlining each of those archetypes, and then we have networks analyzed for each of those archetypes, and then we can do interesting things like what would be optimized networks, looking at all of these different groups of species. So that's where I'm hoping that we can go to.
Mm-hmm. And I remember from the process early on that the three that Sara provided information on today were part of a suite of species that we'd put together, and none of them were species at risk. I mean, that was part of the discussion early on in the 2000s when this was starting to come together, that we wanted to focus on species that either were keystone species like a Townsend's vole would be within grassland habitats, or ones that seem relatively common, but do have particular thresholds for them. So that's why they were kind of like broken into wetland, grasslands, and forest-dependent species. And I think that, as much as the South Coast Conservation Program focuses on species at risk and ecosystems at risk, we also have to be cognizant of the fact that a lot of species that we have been very complacent about thinking of as being very common and widespread are also starting to show marked declines, and that the whole idea about common species as being important indicators, we can't forget about that, because these things tend to be gone, and then we suddenly notice that they are gone and we haven't been paying attention.
Yeah, absolutely.
Josephine, I had a question for you in regards to the mapping. In respect to the change over time, it was really great to know that there is that. So when's the next benchmark of change assessment going to happen? So it was 2009 to 2014, or sorry, 2009 was the original air photo interp
That's
set,
right.
right? And then 2014 was
Yeah, that's right. So we were on we did 5 years. I think it's going to be 6 years next, just because of when we get the ortho photos. We get them every 2 years. So I think it will be using 2020 orthos, and we hope to have a much quicker turnaround with when we actually get it completed and get it out there. This was the first time that we'd done an update, so we didn't really know what we were sort of letting ourselves in for and how long it would take, but we have a much clearer idea of that now. So my intention is that it will be out much quicker next time.
awesome.
And we'll do the land cover at the same time. We'll keep those two tied.
Great. The other thing that I was going to ask you is, I know that in the past we'd done using Landsat. There'd been some analysis work that had been done to try to measure changes in forest cover and wetland communities using even older data. And so, is there any consideration about looking at that sort of vast cumulative change that's been happening, like prior to the 2009 benchmark?
I would love to be able to backcast accurately and be able to say something about loss. It's definitely challenging. It would take quite a bit of work, I think, to sort of rejig those older land cover data sets, for example, to be able to do that. I think the one place where we could hopefully do it is there's the Canadian Wildlife Service and Metro collaborated on a Lower Fraser wetland inventory that was done in 99. Yeah, it was, when was the first one? I'm not sure. Anyway, we redid it in 2009. And I'm hopeful that we can look at again in sort of the 2019 point, using the SCI as a way of helping us make that process easier and update that. So that does have a much longer time frame, looking back at wetland loss at least. But I know, do you want to say something, Sarah? Because I know that you guys do quite a lot looking at older ortho photos and measuring time change.
Yeah, so we have something that's currently under review, looking at a super quick, kind of an oversimplified map of green space change over time for Metro Vancouver, but contrasting it to other Pan-Pacific cities. And so that's kind of, this was part of a study that looked at 15 different cities. So we basically used NDVI, which is a measure of green space, and then used cutoffs for determining what's impervious versus forest versus grassland or shrubs and non-forested but still green space. So we have a rough characterization of that, enough to tell us that compared to several other Pan-Pacific cities, Vancouver's browning, while many of the other cities are greening. But there'd definitely be space to do that in more detail just for Vancouver, and make sure each year is looked at in more detail. Because right now it's one image slice from each year, and so depending on the season of the exact date and green up, there's a little bit of error in that. So I wouldn't use those maps for long-term planning for Vancouver, but it wouldn't take much to tweak them so that they were a little more accurate just for Vancouver. So it's kind of, I guess it's a long-winded way of saying, if you're making a long-term map to compare among 10 different cities, you would do it a little differently than a long-term map just to look in more detail at Vancouver. And so what we've already done is the one that compares across multiple cities.
Great. And Sarah, I have a couple of questions from you, from our attendees. James Casey asks if you can let us know whether or not your work has been written up somewhere that others can access it.
Yeah, absolutely. So two of the things I talked about today are under review. And so they're soon to be published. So the best thing to do is send me an email, check on my website, or I'll probably tweet about them on Twitter.
So,
And James, we can also share our project report, which gives you, it doesn't give you everything, but it does give some initial stuff.
Right. And does that get published on Metrovan's, any of Metrovan's pages, or is it just stuff
that
you
one,
direct send?
Yeah, that one hasn't, just because it's super technical, and there's probably a very limited number of people who actually want to get to that level of detail. We have kind of committee reports that summarize it, but excuse me. But yeah, if you get in touch with me, James, I'm happy to send that along.
That's right. And generally, of course, the SCCP, if you follow us on Facebook, we do try to make sure that when we get new publications of interest, or hopefully the media, especially if they cover it, we provide those updates through our social media connections and through our various pages on our website as well. We have specific pages that are dedicated to resources for local government and citizen science and landowners, and we try to make sure that new publications are getting added to those on a regular basis. Katerina Mazzari also was asking about the water quality end of things. So this is also for you, Sara. She wanted to know what methods that you're employing for analyzing mercury and arsenic in water, and what sort of devices are you using? And I expect she's probably talking about field samplers.
Yeah, so what I didn't really make clear is that we're not doing any of the water chemistry, we're not doing any of the in-stream measurements ourselves. So these are all things from either Carewood Lidal or from Metro Vancouver, who shared their data sets with us.
And so is there, I know with Metro Vancouver, water sampling, and the province used to actually do a lot of water sampling as well in certain priority watersheds. I'm not sure how often they're still doing that. So Josephine, is Metro Vancouver doing regular sampling, or is it just sort of that, I think it was every 5 years for those benchmark watersheds that were part of identifying watershed health within the regional district?
So actually, all of the data that Sara and her team used came directly from our members. So that's the water quality testing that they do. So we're not actually the owners. We sort of act as intermediaries. So it was thanks to their involvement that we were able to use it.
Okay, so I guess it's just based on the capacity of individual contributors, municipalities that are doing that sort of testing.
Yeah, that's right.
Yeah. Has there been any discussion with the South Coast region for the province or Environment and Climate Change Canada, Fisheries and Oceans? I'm not sure who. I think it was ECC who was originally doing it, about becoming more involved in doing water quality testing?
Sara, I think you guys were in touch with them, weren't you, about trying to at least get what they had?
Yeah, it's unfortunate Jenny couldn't be here, so my PhD student. So she has been the key data wrangler for this, and so we've kind of taken a broad brush approach and talked to any people and any agencies that will share information with us, and we're currently in the process of figuring out how much long-term information we have as well, because I think with this first cut we did a pretty good job of getting data and analyzing it for the past few years. But what I think is really interesting is trying to go back further in time, and so she's in the process of figuring out what agencies have which variables and for how long, and that will be our next plan of attack.
Okay. Oh, and we have another question. I'm just answering a question from Erin Clement, but she asked another one about using the ISMP, or the Integrated Stormwater Management Planning report data?
I believe it's the same. So the water quality data that we were usually contacting the ISMP people in the municipalities to get their data. So I believe it's the same.
Yeah, because some of the data from municipalities was already kind of in analysis ready format, like in Excel spreadsheets, but then I believe some of it came from appendices, right?
Yeah, that's right, from reports.
Yeah, from the ISMP reports.
Okay, and just a reminder, in regards to links for all of the good works that are going on through this partnership with Metro Vancouver and UBC. As we get information published, we'll try to make sure that it's available through the South Coast Conservation Program, again, either through social media or newsletter, or posted on our website.
Thank you for that.
Yeah. We're actually pretty good at wrangling, getting stuff published on our website as much as we can, especially if it's no longer available through some sort of archived method, or sometimes we can get permission to get things published that are still kind of in limbo through levels of government, which is useful, getting information out there, because we want to remain current in regards to the conservation science and efforts that are going on that affect the work that we do. So if there aren't any further questions, I definitely would like to thank Sara and Josephine for making time today to share this important work. I hope it's been of use to our attendees. And again, just a reminder that this webinar will actually get posted on our YouTube channel. You can link to that through our homepage, sccp.ca. You don't have to worry about writing down the particular website. And it should get posted within the next week or so. And from there, please feel free to share it. I will make an effort to email attendees for today to let them know that it is posted. And again, we'll post a notification on our Facebook page. And special thanks to the Canadian Society of Environmental Biologists for hosting us today. It's been very grateful that they've allowed us to use their webinar platform. And also to Environment and Climate Change Canada for the Habitat Stewardship Program for Species at Risk funding that has enabled us to actually do this webinar series for the last few years. Our next webinar, which will be the 7th webinar in this series, will be happening sometime in the spring, probably around February or March. Right now, we're in discussions with the resort municipality of Whistler and some of the biologists who are working with them to focus in on the work that they've been doing specifically on developing a species at risk strategy for that area of the sea to sky region. So without further ado, thank you very much for spending time with us today, and look forward to having you join us in the new year, and enjoy the rest of your year, everyone. Thanks very much.
Thank you.
Thanks.